Okay, our next speaker is Julian Rosemann, and he's going to talk about non-interference preserving and optimizing compilation with hyperproperty simulations.
Okay, thank you for the introduction. So I'd like to start with an example. So that should be here. So there's this problem if we have some program here, which is a simple conditional, that we might have non-interference in the source code. But when we do some sound compilation pass, like an optimization, like that code elimination, this might break non-interference. So in this example, we have we assume the leakage model. So non-interference, as you probably all know, is public input equals implies that the traces are indistinguishable from the perspective of some attacker. So in our case, we model as an example leakage model, we use variables that are low or that are secret or public. And we say, okay, the lowercase variables like A are secrets and the uppercase variables are public variables. And we assume that only writes to public variables are observable. Note that this is an example leakage model and our work is not constrained to that leakage model, but this is what we use now. So if you look at this example, the leakage trace in the source program is, well, this one, it's the same on both sides of the branch, no matter how the secret is. These are the two observations that are made. But now, if we look at our example, if we do some dead code elimination, we might eliminate the instructions where the small x is and get a program which is not non-interferent anymore, because now only parts of this leakage is shown, and so the attacker might see what the secret was. So how do we fix this? Let's first look at the related work which has been done in this topic. So the simple case is that if we consider some non-optimized compilation, there often is used the concept of leakage transformers, which was used in the adjustment compiler at the in the publication by Almeida et al. In 2017. The basic idea here is that you assume that every leakage in the source is somehow the leakage in the target is somehow the function of the leakage in the source. And so you can argue, okay, if we can translate every source leakage into some target leakage, which is determined just by the source leakage, we can argue, okay, if the source leakage is equal, then the transformed leakage must also be equal. So that works. Unfortunately, it, for example, it doesn't work on some optimizations like that code elimination, which we will see later on, because there we don't really have this function, because at some points we have some source leakage which will be eliminated, but in other positions it might not be eliminated, and so there's not this function f here doesn't really exist. There's also some work on the special case of the constant time property, which is a special case of non-interference. And there, of course, in the non-optimized compilation, the leakage transformers also work. And some variant of it also works for flow-sensitive optimizations. I don't want to go into detail for that now. But there's also, so as you, sorry, the constant time leakage model is memory accesses are leaked and branch taken status is leaked. And the important thing for us is that this basically removes all secret branches. So we know in the source code already that there is no secret control flow. And there has been also the concept proposed of CT simulations, which basically argue, okay, if we have a source property, which is the CT property, if we want to translate it to the target, we have to do somehow this 2x2 simulation diagram, and we will see that later on as well. And this works even for many flow-sensitive optimizations. So this is largely solved. But what about this case? What if we don't have this strong assumption that there is absolutely no secret branch? So this is what we are focusing on. And the contributions of this work are twofold. So first, we are arguing a little about generalizing simulation proofs. And afterwards, we will show that we have a secure dead code elimination, so a variant of the thing we saw before that is actually secure and preserves non-interference. And we do so by first introducing these three kinds of simulation proofs. Case simulations, which are like a generalization of compilation simulations, where you simulate between a source and a target trace to an arbitrary number of traces. And we have hyperproperty simulations, which are targeted to translate some hyperproperty to a target program. And we have the special case of indistinguishability simulations, which are targeted for exactly preserving non-interference. And then we will show that we can somehow fix our dead code elimination with a technique which basically sounds like it could be used in a more generic way. And it does support secret branches. That is the new contribution here. And yeah, we only did it for dead code elimination so far. And all of this is proven formally in COG, or well, it's now renamed into ROC. So let's start with the first part, the generalization of the simulations. So compilation simulations, the target of a compilation simulation is basically you want to relate the behavior between a source trace and a target trace, and you need to find some invariant which holds at every considered point where these two traces should be related. And you have basically an inductive argument to say, okay, if we have the relation here and we have it on every step forward, we have it everywhere or at every related state. So that's pretty standard. The standard way of using this is, so the basic way is the locksteps compilation simulation, where we just go one step in the source and one step in the target, nothing new here. Now, if we want to generalize this for more steps in the target, because sometimes they don't align very well, then we have this problem, and this is also not new. Everything of this is not new, but the point here is what is the problem here? So the problem. Oh, sorry. So the problem here is we have some simulation relation between source and the target trace, and now at some point every source state is just related to some target state, and we are not making progress here anymore. And in the definitions of these general compilation simulations, this is accounted for by using some technique that prevents this from happening. So we have to somehow guarantee that we are making progress on the target trace all the time. So what is used are like measures of fuel notions. And we define this here by where we have this sync function, which basically says, okay, we are at some point in the source trace. This determines how many steps we have to go in the target trace. And this max stall function argues, okay, how many times are we allowed to stall on this particular spot in the target trace? And we have to have this guarantee that this is so that we really don't stall more often than that, to argue on every point in the trace. Otherwise, we might get stuck somewhere. And this is the thing that we want to generalize for k-traces. Why k-traces? Because we are preserving non-interference, which is a true property. The preservation of it is a for property, and so our approach is now to generalize this concept and introduce our k-simulations, which basically relate an arbitrary number of traces, go some steps on these, and relate them again. So we are jumping from one synchronization point to another. And what are the conditions for that to work? So we use some kind of sync function, which basically takes a position, which is just how much progress we made on every trace. So this is noted by this vector, and says, okay, this is how far we are going on every trace. And so we have this for this first synchronization point, then we get here to this synchronization point, and then again for the green one, we have another vector which is defined by this. But this has to be somehow limited, because again we have to make sure that we are making progress on every trace. So this is how we define our max stall function in this example. So at the first position here, we are only looking here at the first position. We allow the trace 0 not to stall at all. This is noted here. We allow the trace 1 to stall 1 time, and we allow the trace 2 to stall 2 times. And given this functions, we can now define our case synchronizer, which is basically the construct which we use to make sure that our simulations actually make progress all the time. And this has this slightly complicated definition, but actually what it just means is that we make sure that this max stall function really determines on every lane how many steps we have until we are making progress on that lane. And this synchronizer allows us now to define a case simulation, which is defined such that we have our simulation at the start state where the traces are empty, and then we have, okay, if we are in a synchronized state, so the relation holds, and we are also, the position is a synchronized position, so it's basically reachable by our definition of the synchronizer before. And then we are going some steps on the source, which are defined again by the synchronizer. So the amount of steps we are going on every trace are defined by that. Then we know, okay, we are still related in the state where we are heading to. So this is basically the definition of our case simulation. And how do we use it now for our specific context? So the idea is to derive hyperproperty simulations by actually combining different kinds of simulations. So if we are working in a secure compiler, we often have a correct compiler already, or we want that to have anyway. So we have usually a source and a target simulation basically for our compilation paths already. So if we are looking at 2 source traces, so in our picture here, note that the above ones, these are always the source traces, and below we have the target traces. And note that here the colors mean that these are actually the exact same states. So this red one and this red one is the same, and this orange one and this orange one, that's important. And now the setup is the following. Okay, by our non-interference assumption in the source, we somehow have a simulation on the source traces, which is the part above. And also by having a correct compiler, we have some simulation between a source trace and a target trace. And we have that for both source traces that we are looking at. So we have this picture, and now we can combine it, so something like that, which is essentially a force simulation in the context of the case simulation that we have defined before. And one thing that is important here, this only works if we really have, for every synchronization point here, something to match against here, which does work in our example because our source target simulation is basically defined on every source position, so we always have something to match. And now let's look at this. So basically, the CT simulations that were introduced by Butter et al., they are essentially this for a lockstep simulation in the source. So here we have a lockstep simulation. We go from each source state just one step forward. And we basically have a source target simulation here. And this is how they argue to preserve constant time. In our case, this is not enough because this lockstep thing is too restrictive. If we have secret branches, we can't have a lockstep simulation between the source traces because we might go into different branches and you don't have a lockstep simulation there. So what we do is we define the indistinguishability simulation, which basically jumps from every point of leakage to the next one. And since we are assuming non-interference in the source, this is possible. So we can just say, OK, there must be a next point of leakage. And of course, sometimes there is no leakage anymore. Then we are just defaulting to the lockstep. But that is OK, because then there can't get anything. There is nothing that can go broken, because the target program will also don't have any leakage there anymore. And so now this is the technique, the distinguishability simulations that we use for our proofs. And now let's see how it does work in practice. So in practice is maybe an overstatement because we are only working with some toy language. But OK, so the basic idea here is the interesting thing is to think about the conditionals. How are the conditionals handled? And basically, there are three cases. So first, on the left side, we might have a public branch. So the variable here is, the branching variable is public. Then we don't have any problem. Then we are basically in the case of the CT simulations. And we can actually do the dead code elimination aggressively, because we know that if we are considering two source traces and two target traces, they must both take the same way, either both left or both right. So there's nothing that nothing observable to see. And then we have the case where we have a secret branch. And there, what we do is we basically try to do the aggressive optimization. So we try to eliminate all dead variables. And then we check at the end of the branch whether we've done the same, basically the same changes in the leakage. If yes, then this is fine. So in this example, we can do this. We can eliminate the x, the one written to the x on both sides, because afterwards we still have the same leakage traces. And if no, we have to use some kind of fallback path. So in the case of dead code elimination, this would mean either just don't do dead code elimination, or you could just restrict it to non-leaky variables in that sense. And yeah, that is how it works here. And the interesting thing here is that this fallback is always local. Basically, if we have to fall back somewhere and can't optimize this construct, this doesn't mean that we can't optimize other stuff. So it doesn't affect the whole program. And then on loops, this is less interesting because, so in the public context, we can do the same thing. If we have a public context and the public exit condition, we can optimize aggressively. And otherwise, we actually can't optimize leaky instructions, because this tracking approach of what has happened breaks as soon as we have some secret exit condition. So there's nothing to do there. So now let's conclude this talk. We have this picture from before. So our technique of indistinguishability simulations basically works in every case here and fills this gap. And then, so our contributions are that we have introduced and formalized in COG these three new, three kind of simulation proofs, which are the case simulations, hyperproperty simulation, and indistinguishability simulation. And we have formally proven this fixed version of that code elimination, where we use the indistinguishability simulation to do the proof actually. And future direction could be, is this scheme that I've presented here generalizable? So it couldn't be do the same kind of fixing of the code elimination. We probably can do it for more other optimizations. And then our introduced techniques, there's the question, are they useful in other properties or contexts? And yeah, that's basically how I want to conclude my talk. Thanks.
Thank you. Nice talk. I mean, that's a grand feat unlocked talking about case simulations. And the floor is open for questions.
I think it was turned on before.
Yeah, I think it works. Thanks. Thank you for the talk. I was just wondering, very short question, but the notion of two simulation that you generalize, is that the same as stuttering simulation? Or do you know what
do you mean by stuttering simulation?
Yeah, so stuttering simulation is like, you know, in the standard textbook of like Joost Pieter Katoen, right? The book on biosimulation and so on. He defines stuttering simulations and then also diversions sensitive stuttering simulations.
Mm-hmm.
And they seem to be about, they seem to be very similar in the sense, well, that's, but in the sense that they allow one trace to do multiple steps, the other one to stay in the state, and then it's diversion sensitive, means that there should be some, that they cannot both, that it cannot be the case that one stays where the other infinitely loops, right?
Exactly. It's
so I was just wondering if this two simulation that you generalize is the same thing, or if there's some subtle difference that I'm not thinking about.
It's the same thing. Yeah.
Okay. Yeah. Thanks.
Also to that question, there's a 2023 paper called Stuttering for Free. There's a 2023 paper called Stuttering for Free, and it also talks about that topic. I have another question, and it's about the language you use. It has to be deterministic so that you can get the sync function defined, right?
Yes, basically yes, but you could work somehow with a random tape as modeled and use it in as a separate input. So it's not really restricted to that, but we are working with a deterministic language, yes.
Okay, thanks.
Thanks for the talk. So in the two simulation world, there's a way to do these stuttering simulations without having to explicitly write down like these sync functions and counting and things like that. Just having a least fixed point in the simulation relation definition, and then you get like a. I think that's also the core of stuttering for free. That has existed before that as well. You end up just being able to do finitely many stuttering steps, and it has to be finite, but you never have to write down the number, which is much more convenient. So I wonder, do you think this could work as well here? Like it gets a bit more complicated because the notion of synchronization point becomes more complicated. And I'm not sure if it's even necessary to say you always have all functions, all threads synchronized. Maybe you have the first two and then the last two or something. Or I don't know how general this gets. But I'm wondering, is this something you thought about, or why you picked this like very explicit counting representation for the stuttering?
So I picked this counting representation because it somehow works easily to like add up the position where like the step to the position, and you can do inductive proofs on that. That works quite fine, but I think it might work, yes. So my intuition says yes, but I haven't thought about it too much.
Okay, yeah, thanks.
More questions? I have one simple question. So what kind of other optimizations are you thinking about?
So what we are thinking about, for example, is common branch factorization to make an argument that we are not restricted to like keeping the same control flow. But this should also work because if the if the branch itself leaks, then it might not be legal to do the optimization there, and so we have to restrict it somehow. But we can also maybe argue that if we just swap the leakage, this is also fine. And I think it should work because basically the key of the indistinguishability simulation is that we really just look at the points where we have leakage and can ignore everything else, which makes things a lot easier.
Well, if there are no other questions, let's thank the speaker again. Thank you.